Good morning. My name is Mudassir Sharif, and in this part of our presentation, which is related to artificial intelligence topic, we are going to discuss two different scenarios. They are basically related to our previous presentation of artificial intelligence part 1. If you didn't have the time to listen this presentation, then it will be good to have a look at it. So let's begin. In this presentation, we are going to present two different use case scenarios from our state-of-the-art environment that we have developed here. One of the use cases is related to electric vehicle application, smart to charge electric vehicle smart to charge application, where we are going to distribute resources optimally. In the second, we are going to present sound classification, environmental sound classification using deep learning, and this time it is represented automatically done. So let's get started. For example, we would like to start it with some basic scenario that might be faced in our real time forever. It might be possible that you already face this scenario, so let's discuss about it. For example, your city council of Stuttgart that would like to organize an event, and this event can be different. It can be a yearly event, it can be a monthly event, or like 2 times in an year event, where there a lot of people are participating around the country or around the region from different countries, and they would like to participate inside that event. And the most probably, if the people they are participating around within the country, they are using different mode of transportation. Some people use mode of transportation public, and some people come up with a private. With the private mode of transportation, they would like to use their different type of fuel they would like to use. For example, electric vehicle, kerosene and diesel or petrol, etc. But here we would like to discuss more about electric vehicle. So, for example, there are few events, something like a football event where there are a lot of people around the globe are coming, and some are participating within the countries from some remote locations. They are using their private transport because might be the event will be ended very late and they don't have a really good way of transportation. But it is also possible that on the other hand, state would like to organize this event. They would have to done everything really actively in order to give their audience a better experience. Similarly, like there is also an event in Stuttgart. It is a kind of this event occurs after winter, at the end of the winter and at the start of the spring. And this event can a lot of people, this actually event give you a kind of joyness, and a lot of people around the Germany, they participate in that event. Around this event stays around 15 days, but every day at peak times for the start and the ending, it around 1 lakh people participate every day in this event. There is also possible that the organization is doing some sort of Christmas event and Christmas markets. So at the night, the people are coming and joining it. Moreover, there is also possibility that the cities are recognizing some conferences, some digital organization events where the people are participating around the globe, and they would like to, and there are a lot, inside this exhibition, the people are coming from the cities, they would like to participate inside it. These are such type of example, but there are a lot of other example as well. For example, in the first user scenario, I would like to say that there is a person like Tina. She lives in Tübingen and on his own electric car, and she would drive her car toward the Stuttgart, which is not far from her located city. But she would like to know that is her car have a capability to be there, while if it doesn't possible, then she would like to know that what are the possibility of the charging station, what are the charging prices, how much for the charging station from that location where she is gonna attend the event, and how much time is charging station would take to charge her car, and potential service disruption if there is some downtime in charging station, then what are the possibilities or help she can get during that time. On the other hand, it is very important for the point of a local grid operator. Here we have just represented person Wolfgang. So he would like to know that how it is possible that he has to maintain the electric energy up and running and according to the formation forecast. It means that how much cost it is required and how much manpower he has required to generate it, to operate it and available for their end users, and they don't want to produce more energy rather than consumers consume it. And the same time, the fleet operator would like to know that how many people they came via public transport, but they would like or interested to hire some car sharing fleets, and they book their private fleet on the way back, and all the things which is related to the fleet operators are available, charging schedule tariff, and also battery type, energy type cost, then it will be easy for the end user to calculate overall cost for it. With respect to all these user scenarios, we have developed electric vehicle end user scenario where the electric grid operators are participating, and the fleet operator are the participator as well, and charging station maintainer. This information, they are the input parameter that are important with respect to the each stakeholders, and all these parameters are given to the model, and models have certain states. X1, for example, daily travel activities X1, having a rand reward, at the first time it has a random reward, and then it will be calculated according to the objective, and then the action will be taken according to the calculated objective, and then it observe the state, and then this will continue until the appropriate training is done with respect to the available data set we have. And at the same time, when we have billions of participants or million of participants, we would like to calculate these things, and it requires a lot of computation power. In order to reduce the computation time, we have deployed these services over number of interconnected nodes called high performance computing nodes, where all this information is calculated and then available within few seconds as per the requirement of the end user. It is really highly recommended that if you haven't reviewed our first session, which is related to artificial intelligence general builder, then it is very important to review that, where we have already presented deep reinforcement learning architecture. So at the moment, I am only closing these things with respect to the electric car perspective. Electric car is running on the electricity, so it means that it also requires some energy, and the electric provider have to be able to provide that energy towards a specific charging station. So it is possible that the charging station maintainer will also participate inside it. There is also possibility that this car is bought from some car sharing companies. It is not his or her own car, so the car sharing company also be a part of it as well. And at the end user would like to calculate the overall cost, and would like to see that either it will be suitable for him to participate with his or her own car, or it will be good to have a participated with the rented car, where the more people he can accommodate and come and go through with participate in that event. It all depends upon the actual requirements of the end user. Here we have presented that if the car at this location XY, then this charging station is suitable for it. At this location P3, at point P3, that will be suited for this charging location. And they have a different objective X or Y. It means that at certain objective, this location is optimal cost he has received. At this objective is this, at this point it receives this. So it's context aware optimal resource distribution. Here is a more detailed example we have done at this location for electric vehicle. It shows that these 3 charging stations are more suitable for it, and it gives these are the 4 charging stations that are at the moment over here, and at this location they are these charging stations where the optimal cost is suitable for it, then it will select that one, and same for here as well. And at the end, we have given an optimal cost calculation graph that represented for the electric vehicle architecture. On the left-hand side, we have static location that we have pointed charging station over there. And on the right-hand side, we have optimal cost at each charging station. At the end, at the bottom of this graph, we have electric vehicle at point XY, and electric vehicle at point P2, X2, Y2, and at the 0.3 XY. So there are the 3 different locations. At this location, we have got a right optimal cost for with respect to our end user at charging station 1. And over here we have got the optimal cost for the charging station 3. And here we have got at the charging station 4. These colors represent the charging station over here as well. Or green, it is charging station 1. At point 2, the charging cost for the charging station 1 is high, and here it's kind of a little bit higher than at point P1, but you can see the significant difference, but it also depends upon the charging points with respect to the end user requirement. So we are not going to calculate the minimum cost, we are going to calculate the optimal cost that depend major on the factor that is selected by the end user. Here you can see some text, it is in black in color. I'm sorry for the, you cannot see the topic name, but I can say I can read it for you. It's iMobile Acco. It means that intelligent mobility using acoustic devices. This is the second topic that we would like to discuss about mobility using sound acoustic, and we are going to classify between different vehicles, and you will see in the next slide why this topic is really popular, and it is getting much more attention these days. And here we have certain outline that we have designed for it. We have at the end problem formulation, why we chose this topic, what problem we have faced at the start, what problem occur in our real world for our real inhabitants, and what is the objective of this topic, and what purpose we have, what architecture we have proposed for it, what user scenario we have taken, what are the performance analysis we have done, and conclusion and future work at the end. So let's jump into the problem formulation. Suppose that you are living in a condensity area like Copenhagen, Stockholm, London, much more such type of city that have intense traffic, which produce a lot of sounds or noise, which is unbearable for few people. It's true, every 5th people that live around us is suffering from noise cancellation, noise pollution, not cancellation, noise pollution. So recent studies show that noise pollution is one of the biggest challenge for cities that are situated inside the valley. It is getting more worse when the cities are inside around the rock and around the mountains, and they are inside inhabitants living inside it. There is also another problem faced by city of Stuttgart. They have reported a number of complaints from citizens that they are facing noise level problems, and They offered a research grant to the IF research team in University of Applied Sciences in Stuttgart, where they have developed iMobile OCO to overcome noise level challenges. iMobile is intelligent mobility using acoustics, and we have used sound acoustics to make mobility more flexible. What is our objective? Our objective is to reduce the problem of sounds with certain different techniques that can be used. We have here recognized automatically sound audio patterns of environmental sound, can be car, engine, human speak, nature, etc. And to check that what type of sound is majorly problems, most probably the traffic. When we have a vehicle, some small vehicle, they can be passed easily, but for large vehicle, when they stuck in traffic, they produce more sound and it can generate a lot of sound when they are stuck. iMobile OCO is using machine learning to detect vehicles using sound acoustics. So here we have a proposed architecture. At the left hand side, we have environmental sounds that we in the form set of sounds file. This sound file consists of 3 to 5 second sound file, and we have prepared our data before giving it into the machine learning model. And here are the pre-processing steps that we have done, and then we have a feature in digit format. Then we give all these features over here to our input layers, and that is forwarded to our hidden layers and then calculated at the end. We have a output. Sorry. And this process is we have done automatically with the help of GitLab continuous integration and continuous delivery and continuous deployment. So whenever we have a new sound feature occurs, it automatically learn, read, and then predict it. If you don't know more about or you would like to learn more about continuous integration and continuous delivery, you can follow up this paper, and or you can go towards internet, online over the internet, and then search for CI/CD pipeline. Here are the 3 different scenarios. For example, we have a scenario. This is the actually real map of the city at the peak time, where the traffic something like this, and something like this, and something like this. And it can generate, here is the heat map of this sound generation with respect to the decibel, and this is the map that's illustrating the noise pollution at that peak time at the main road or inside the city. So we have implemented this scenario with device operating system Microsoft Windows 10 64-bit at the start, but it promoted more and more, and then we deploy it over our high performance computing nodes, and then we have used programming language Python 3.7. We have used machine learning library TensorFlow. We have used API Keras for TensorFlow. We have used LibreOffice for feature extraction. You can use other libraries as well. They are available, but according to our research and literature, we found this one is really helpful. We have used visualization toolkit for machine learning, TensorBoard, and we have used dataset at the end, FreeSound 50K dataset over there. Here we, on the right hand side, we have a, for example, one sound wave file. Using LibreOffice, we get the feature, extracted the features using LibreOffice library, and input this feature into our model that are fetched and calculated at the end. We have a one selection of this car is lightweight vehicle because it's car.wave file. So at the end, it detected lightweight vehicle. If you would like to know more about, you can go over there and you can learn more this about this research. Here I have just drawn out the generalized model with all the number of inputs, outputs that we are going to detect. Lightweight vehicle, medium weight vehicle, heavyweight vehicle, rail-bound, two-wheel vehicle, and if it is not other, which can say a horn sounds, a bird voice, and some other sounds that are not part of this acoustic mobility, they are in an other layer. Performance analysis, it is very important how our model predict, learn, behave during it. We have tested it in a number of augmented data sets. With respect to 750 file, it gave us 97.83 accuracy and minimum at different interval it gave maximum 85 and 3 minutes 26 seconds, and augmented data set for 2750 files give us this information, and similar for FSDK data sets. They are all publicly available. You can download it and see. We have our accuracy increase, but we have also more time because we have large data sets. And when we use millions of file data sets, then it is important that we have to give the answer to our end user as soon as possible, rather than it took hours. So in order to avoid this problem, we have deployed our solution over high performance computing node there, where the system is learning at parallel time and then predicting the results. So model accuracy, it's very important how your model accurately detect the features and predict it the right things. And we increase our noise. This is the noise factor here, and it's the model accuracy. At minimum noise factor, we have a accuracy more than 82%. And then when we have more noise factors at larger data sets, accuracy is almost about the stable, but the noise is continuously gradually increase. So, but still our model behave really well at this noise level as well. I would like to thank you so much for this, for listening us, but still we have one more slides before we can say goodbye. For this topic, this is really important. What we have done, how we will close it, and what will be our future work. In conclusions, we have found that this information will be helpful. It can be helpful for the urban planning, for example, building smart buildings and mobility experts in order to mobilize their traffic. Training time can be reduced with parallelization techniques, and that we have already done in our new methodology with more large data sets using deep reinforcement learning strategy. But in this model, we have only used deep learning, but in our future model, we have used deep reinforcement learning methodology. If you don't know about this methodology is continuously available, clearly available over the internet. You can just go from it. Otherwise, it is also possible for you to look at our first part of the presentation. We have explained about deep reinforcement learning. I would like to thank you so much for your cooperation, for your listening us. Thanks. Have a nice day. Take care. Bye-bye.